Okay, hello everybody. So, part A, explain how to compute the dot product of two vectors. Okay, so if v equals v1, v2, up to vn, and w equals w1, w2, up to wn, then v dot w is equal to v1 w1 plus v2 w2 plus all the way to, vn wn, which you can write as the vi wi, where there's n terms in your sum. That's it. This is how to compute the dot product of two vectors. B. Explain how the dot product relates to lengths and angles. How does dot product relate to length and angle? Well, v dot w is equal to the length of v times the length of w times the cosine of the angle between them. And I'll just explain my symbols where theta is the angle between v and w. And the length of v equals the length of v, which is defined to be the square root of v dot v. Similarly for the length of w. Okay, so yeah, this is the relationship between the dot product, which we compute like that, and the geometry, namely lengths and angles. C. What is the dot product on space-time according to special relativity? Okay, so if space-time were flat R4, by the way, I'm just putting this in there so you see it, and so you know that the dot product you can tweak it and change it, but it's roughly the same thing, although the changes can result in very different behavior. For example, special relativity. So if space-time were flat R4, then we'd say that v dot w is going to be v1, basically the same as before, except here we have a minus sign, and that's it. Sometimes you might put a minus c, where c is the speed of light. But this ends up being the dot product, I'd say, in special relativity. Okay, and by the way, if you take v dot v, like a vector dot with itself, and say that it's equal to 0, then in the three-dimensional case you get the picture that we had in a previous problem, namely like hyperboloids like this, and inside there's a cone. This is the light cone. Photons are the only things that have dot product 0. What I'm saying doesn't really make much sense, but if you learn about special relativity, you can make it make sense. Okay, part D. So this is all. I just want you to know that you flip this is the time, and then this is the space. So you flip one of them to a minus sign. Actually, in physics, they sometimes put all these as minus. They somehow put all the space as minus and keep time positive, but it doesn't matter. D. What is the dot product on wave functions in quantum mechanics? Okay, so again, I'm not seriously asking you. I just want to show you that the dot product can be changed a little bit, and you get some interesting stuff. So in quantum mechanics, the vectors, or let's say the wave functions, are vectors in an infinite dimensional space, usually. unless qubits and quantum computing sometimes has finite dimensional spaces, but usually it's an infinite dimensional space. And the sum of the VI, WI changes to an integral. And what's the integral? Well, usually it's something like the integral of the v of x, w of x, where x varies all over space. And then, this sum changes into an integral. And when we learn what integrals are, which you've already learned in Calc 1, integral is sort of like a sum. It's like an infinite version of adding things. And instead of the components of the vector, we have infinitely many components, like the values of a function. There's one more thing. You have to use the complex numbers, not r. And so then you have to do a little flip. This is a complex conjugation. And this is the dot product of v and w. Okay, so really just, the finite sum becomes an infinite integral. And you see that it's not so much different, this dot product. And it's still very important in quantum mechanics and special relativity and really everywhere.